Okay, so last class we talked about describing motion. In particular, we focused on different ways of looking at position, velocity, and acceleration. Today, we're going to look at a very special case and do some problem solving using it. And the special case is constant acceleration. Right? And to indicate that it's constant, I will use the letter A with a little c as a subscript. So this is reasonably important. There's a fair number of cases where the acceleration is constant. In many other cases, it's approximately true. But more importantly for this course, we can do everything mathematically very simple. All right? So the basic idea is A, the acceleration, is equal to a constant. That's all we're saying. And when I say constant, I mean it does not change with time. Okay? And the usual example is acceleration on the surface of the Earth when there's no air friction around, or where air friction is negligible. In that case, the acceleration is pretty close to being constant. Also, when you drive a car, to a large degree, when you put your foot on the brake or you put your foot on the gas pedal, you're accelerating at a reasonably constant rate. All right, so that's a reasonable approximation. Question is, if this is the acceleration, how does the velocity vary with time? To answer that, we recognize that A is dv dt, and that has to equal acceleration. So here's our v right here. Okay, so somehow we want to find v as a function of t rather than dv dt. So the question is, what function, when I take a derivative with respect to time, gives me a constant? Okay? Now, if you know how to integrate, you would just integrate this equation, but many of you don't, so we just guess the answer. All right? So what function would do that? This is the function that will do that. So take a look at that, and you notice that if I take the derivative of this function, so the derivative dv dt over here, the derivative of constant is 0, and the derivative of something, a constant times t, is just that constant. So sure enough, this works. All right, so I have the answer. Now, we'd like to give some physical meaning to that constant. And the way we do that is note that v at t equals 0 is just equal to the constant. All right, so it's natural to just call that either v0 or sometimes v sub I for initial. Okay? So we get the formula v at some time t is equal to v0 plus the acceleration. Now notice, when I write v of t, I'm thinking of it as a function of time. I'm not multiplying by time. So now we have the velocity as a function of time. Now we can easily do this again to find how the position varies with time. We know that ds dt is equal to v, and we just figured out what v is. It's v0 plus act. All right. So now we want to find out what s is. So what do? We guess again. So the question is, what function, if we take a derivative, will give me this? Okay, so the answer is, so this implies s is equal to some constant. There's always a constant, plus v0t plus 1/2 act squared. Okay? So let's see if this works. So I take the derivative of s, and I want to get this formula. So the derivative constant is 0. That's good. The derivative of this term, v0 times t, the derivative with respect to t is v0. There's my v0. And the derivative of this term, how do you get that? Well, the derivative of t squared, hopefully you know from calculus, is 2t. The 2 cancels the 1/2, and I'm left with t times ac. So sure enough, that works. And again, we notice that s of 0 is equal to the constant. All right? So we just set that constant equal to the initial position. All right? So this implies s equals s0 plus v0t plus 1/2 ac t squared. All right? So there are 3 different constants in this formula, but they really mean different things. S0 is the initial position, v0 is the initial velocity, and ac is the constant acceleration over that whole range. 2 equations. We have v. Let me bracket them. This is an important one that you should memorize. This one's another one. Okay. Now, sometimes we don't know or we're not interested in the time. So I can solve this equation for time, and stick it in here. Okay, so these 2 equations here lead to the following equation. V squared equals v0 squared plus 2ac s minus s0. Okay. So we now have 3 equations that are very useful. And sometimes this one's very useful. I strongly urge, if you're not sure about this, that you do the little bit of algebra to take this equation, solve for t, stick it in here, and get that. Okay, I'm not going to do it here. So we have 3 equations. These form the foundation for any problem we want to solve where there's constant acceleration. So let's do the example that we did, I think, in the first class. Namely, how much time does it take for an object to fall? All right, so time for an object to fall from a height h. All right? Now, if you remember, the answer turned out to be proportional to or related to the square root of the height divided by g. All right? So the first thing to do whenever you have a problem, step 1 is to draw a picture. So we draw a picture. Here's our object, and it's falling. All right? And how far is it falling? At distance h. So it's good to write in what we know. The initial velocity, v0, is 0. S0 is equal to h. And everywhere here, the acceleration is equal to minus g. Minus g. Now, you can call up positive, down positive. You can do it either way. I find for myself that always calling up positive and realizing that the acceleration is negative, minus g, makes life so much easier. All right? That takes into account almost all situations. I have found that when students decide to call down positive, in some cases it makes life a little easier, but it also leads to all kinds of confusion and mistakes. So I urge you to choose up as positive. All right? So the question is, we have this. At the ground, S is equal to 0. We'll call that our 0. And V, we have no idea. We have no idea what it is. So we're interested in the time it falls. So we should look at the equations with time in it. This one has it. This one has it. But we're interested in the time it fell over a different particular distance, h. So it looks like this one's probably the one we want to use. All right, so we just use that. We follow with this. We have the final position is 0. All right, so that's what S is, 0. The initial, and that has got to equal the initial position. So this is S0. This is S. Plus 0, because V0 equals 0. Minus 1/2 gt squared. So this is AC. So we have a simple formula. We can now easily solve it. And we get T equals 2h divided by g square root. All right? And of course, the positive square root is physically meaningful. All right? So we've calculated the formula. Dimensional analysis did not tell us about this too, but the actual theory, the formal theory, tells you it. Now, another kind of problem we want to do is where the acceleration is constant, but not in every region of motion. All right? So a good example of this is the following. You've probably seen this in movies. I always find it amazing. Whenever the hero jumps out of a window of some 20-story building, there's always a trash dump at the bottom that he falls into. And somehow that saves his life. Well, let's look at the physics of that and see how that might work. All right? So here's the situation. I'll just draw it. You start up here at some height h. Okay? And then we'll imagine your trash dump over here. All right? And let's say it has, some thickness. Let's call it, let's give it a name. How about W? Okay? All right? And you start out at the top here and here. Right here, AC is G, minus G. What's happening over there? Well, to a good approximation, we can assume that the acceleration is constant, or at least there's some average acceleration. All right? And then the question is, what is that acceleration? What acceleration would work to stop the person by the time they got to there and then reached there? Okay? First of all, what direction is that acceleration? All right? Well, the acceleration here is going to be some acceleration. And since it's going this way but slowing down, this acceleration will actually be positive. It's going to be up. All right? And we should probably give it a name. Let's give it a T for trash dump. All right? So that's the acceleration there. It's constant. All right. So here's what we do. We draw a diagram. That's always what you do. Then on the diagram, you indicate all the interesting points. All right? So one point is the initial position. So the initial position up here is h plus w. All right? Its velocity up there, v0 is 0. All right, so we've done this part here. What about this point? Well, we'll give this a name. We'll say this is S1, and S1 is equal to W, right? Because we'll call this the ground to be 0. V1, we have no idea. Right? Then finally, we have S2, which is over here. That's the ground. We'll call that 0. And V2 is equal to 0 because the person has come to rest at the bottom of the trash dump. And the question is, how does this A here depend on H and W? All right? So that's what our question is. All right, let's solve this. Well, we can't quite solve it directly. It looks like in order to figure out what's going to happen, we first need to know what V1 is. All right? Because we don't know what that is. Once we know what V1 is, then we can use this and solve for AT. The other thing is, we're not interested in time. Time's not an issue here. We really only want to know what AT is, and we have all this position data. So that suggests that this might be the right equation to use. So let's use this equation to get V1, right? So we have V1 squared is equal to V0 squared. Well, what's the initial velocity from here to here? The initial velocity is 0. What's AC? Well, that's minus G. All right. S1 is W minus H plus W. All right, so this is my S0. And this is S1. All right? All right, so we now have everything. Let's simplify a little bit. We get V1 squared is minus 2G times W minus that. So W minus H plus W. The W's cancel, and I get minus H. All right. Now here's an important lesson. If I did my algebra right, the right-hand side better be positive because the left-hand side is positive. If I did it wrong, or if I set up my equation wrong, I would get a negative sign here, and I know I made a mistake. All right, so this is one thing that is really key to problem solving. You not only get an answer, but you have to evaluate your answer to see if it makes sense. So at least this makes sense. All right, now I could solve for V1, but actually I'm not sure I need it because I want to use this same equation here, but I want to use it from here to here. And again, I don't care about the time, so I might as well just use this equation here. Okay? All right. So I want to find, I know V2 squared is what? Well, it's 0, because I have this. V2 squared is 0. All right? And that's got to equal the initial velocity for this part of the motion. Well, the initial velocity here is V1. I just calculated V1 squared, and that's what I need. So it's 2G. Then I have 2A times this trash acceleration, the acceleration due to the trash bin there. So I have that. And then I have to write in S, which is 0, minus W. So that's what I have. All right, so I have this minus W, and I want to solve for AT. I want to see what AT, how it depends on everything else. All right, so if I do that, I get AT is equal to the 2's cancel, so that's nice, and I get GH divided by W. Okay? All right. Once again, everything has the right sign. My acceleration is positive, which is what I expected. All right? And that's key because I have that minus sign over there. All right. Let's check the units here. Well, the units of H are the same as the units of W. They're both lengths. So the acceleration is just a factor of g. That's good. So let's make this realistic. So supposing, let's take a 20-story building. All right? And W is roughly about a trash dump is about like this big. Let's say that's about a half a story high. So let's say W equals a half a story. So all this implies that the acceleration will be g times 20 divided by half, or 40. That's 40 g's. That's a pretty big acceleration. I don't even think the astronauts going up on space experience 40 g's. That's pretty big. All right? So this is pretty unlikely that this is going to work. So a 20-story building into a trash dump is not likely to lead to no injuries whatsoever. You might survive, but it's going to be pretty uncomfortable in the process. So let me just summarize briefly. When you have constant acceleration, step number 1 is to draw a picture. Step number 2 is to identify the key places on that picture where you might know something about the motion, and put in what you know. That's step number 2 or 3. The next step is to decide which of these three, and it may be more than one, which of those equations are useful to use to solve the problem. All right? And it might be that you have to do, usually if there's more than one region like this, you'll have to do it in more than one step. Okay? And then the final thing is to do the calculations and to make sure your answer has the right sign and the right units in them as well. So next time, we'll learn about how to expand this way of thinking into more than one dimension.